Write the expression as a decimal and as a percent. As a percent, 57 out of 100 would be 57%. As a decimal, we would move that decimal 2 spots to the left, so that would be 0.57. You can do the same thing to change these into percents using the cross multiply and divide technique that we've been using for percents back in Module 5. And then move the decimal 2 spots to the left to turn it into the decimal version of the percent. If we toss a paper cup into the air, what are the ways it can land? It can land on the bottom, it can land on its top, or it can land on its side. Adjust the tape diagram to show how likely you think each outcome is. Label each section with likely, equally likely, or unlikely. I think that it'll land on its side more than it'll land on its top or bottom, but I think those two are pretty equally likely. So the right side up, I think, is unlikely. Upside down, I think, is unlikely. And on its side is likely. But I think these two are similar to each other. Shooting a free throw in a basketball game is a chance experiment. What are all the possible outcomes from shooting 3 free throws? Well, you can make it, or you can miss your shot. Rolling a standard 6-sided die is a chance experiment. What are all the possible outcomes when rolling this die? You can roll a 1, a 2, a 3, a 4, a 5, or a 6. Which outcomes of the chance experiments are even numbers? 2, 4, and 6 are all even numbers. Spinning a spinner is a chance experiment. What are the possible outcomes when spinning this spinner? You could land on a 1, 2, 3, 4, 5, 6, 7, or you could land on 8. The list of all the possible outcomes is called the sample space. Consider a chance experiment where you randomly choose one of the 10 numbered squares. Change the color of each square to blue, red, purple, green, or yellow. Try to select an order of colors no one else in the class will create. Suppose we randomly pick a square and record the color of the square we pick. Suppose we consider an event to be selecting a square of a particular color. In the table, list the outcomes that lead to each event. So if we're picking a blue square, it could be 1, or it could be a 3. For picking a red square, it could be a 2 or a 4. For a purple square, it could be a 6 or 7. For a green square, it could be 5 or 9. And for a yellow square, it could be 8 or 10. If you selected different colors for your squares, your numbers need to match the colors described in the events. These colored squares were randomly chosen. In the table, list the outcomes that led to each event. For the blue squares, this was 3 and 10. For the red square, 2, 8, and 9. For the purple square, 4. The green square was 6. And the yellow square is a 1, a 5, and a 7. What is the sample space of the cup experiment? What outcomes are included in the event that the cup does not land on its side? The sample space would be landing right side up, upside down, or on its side. Since those are the list of all possible outcomes. Then it says what outcomes are included in the event that the cup does not land on its side. If it does not land on its side, the cup could either land right side up or upside down. So on its side or upside down. Toss a paper cup 30 times. Use the table to record the frequency of each outcome. You can use the cup counters to keep track as you go. If you have a paper cup or a plastic cup at home that you can toss, you're going to keep track of which way it lands, and that'll adjust your table accordingly. So you're tossing it 30 times, recording each way that it lands all of those 30 times. This is something that you will want your data to use for the next couple of slides. So go ahead and complete that experiment now. Here are my results from my experiment. You can see that the total number of tosses added up to 30. What is the empirical probability of a paper cup landing on its side? So we're taking the side number, which in mine is 18, and dividing it by the total number of times we completed this experiment, which would be 30. The number of sides or times it landed on its side might be different in yours, but the bottom should say 30 because you were to complete the experiment 30 times. For landing upside down, you're going to take the number of times that it landed upside down and divide it by 30, because again, that's the total number of times we did this chance experiment. Then landing right side up, take your right side up number divided by 30. And then it says the total number of flips for the entire class is, and it's going to change based on if your peers have completed this. Based on the data you collected, predict the counts for the entire class. Let's say, for example, that your class had 9 groups. So then each group would have completed this 30 times. So we should have a total of 270 flips for the entire class. Then it says, based on the data you collected, predict the counts for the entire class. Well, we predicted that 5 out of 30 would be right side up. So if we're changing our total from 30 to 270, we can figure out what the equivalent fraction is for that. Same thing for the upside down version, as well as landing on its side. You can either use the cross multiply and divide technique like we did for percents, or you can multiply 30 times 9 makes 270. So 5 times 9 would give us 45. 7 times 9 is 63. And 18 times 9 is 162. We can double check our math by making sure that when we add these 3 values together, we get a total of 270. If the amount your class has completed is different than mine, you'll need to make sure that your denominator matches that. So then they're going to have the actual results from your classmates. Since I'm the only one doing this lesson, it's just my numbers from before. But had we had 9 groups, they would show the actual results from the 9 groups. Let's imagine our numbers came out something like this. It says, do the class results match your prediction for the entire class? And why? Well, my prediction was 45 and the actual results was 52. So no, my results do not match the prediction and the reason is because this is a chance experiment. It's not going to come out perfectly based on one experiment, but our numbers are pretty close. We can see that it's not very easy to predict the exact result for an entire class because every time we flip the cup over or toss the cup, there's a piece of chance involved. The more that we do these experiments, the closer we are going to get to a more accurate prediction. Instead of tossing it 30 times, if I would have tossed it 50 times, I may be able to make my prediction even closer. But every time we flip that cup or toss that cup, there's a piece of chance that's involved. Based on the class results, how many times do you think a student's cup will not land on its side if they throw it 10 times? In our class results, if we've combined the amount of times it's not on its side, that makes 97 out of the 270. If we use those results and compare it to only 10 times, if you cross multiply and divide 97 times 10 and divide by 270, you get 3.59 and so on. But you're going to round it to the closest whole number because you wouldn't throw it a half of a time or a partial time. So this would be approximately 4 times where it would not land on its side out of the 10. For chance experiments, the probability of it landing on the side, the top, or the bottom is based off of your experiment. There are actual values that we would use for the probabilities in theory, but for these empirical statistics, you are using the values from the experiment.